Welcome to this lecture series in linear algebra. In this lecture, we'll learn about some relationship between the geometric and algebraic multiplicities of the endomorphism induced on the quotient space formed by a T-invariant subspace and the algebraic multiplicities and geometric multiplicities of the original endomorphism. We will state everything precisely. So what we need to know to follow this lecture is quotient spaces. We have been using quotient spaces frequently, so there is no need to recall. It's a fundamental thing. Then again, another fundamental fact is that if you have a T-invariant subspace, T is an endomorphism on V, and you have a T-invariant subspace, then there is an induced endomorphism on the quotient space. And we have been making this diagram since the beginning. So this diagram commutes, and all of these things we will use. And let us recall the definition of geometric and algebraic multiplicity of an eigen polynomial. So if T is an endomorphism on V and Px is an eigen polynomial of T, then the geometric multiplicity of P is defined as the dimension of the kernel of this endomorphism, and the algebraic multiplicity is defined as dimension of the kernel of this endomorphism. We gave a slightly different definition, but we commented that it is equivalent to this. Alright, so these are definitions of geometric and algebraic multiplicities. And it is clear that the algebraic multiplicity exceeds or is at least the geometric multiplicity. So let's go ahead. So before we get to the main theorem, we need to, it's good to establish some basic facts rather than leave them as exercises. So let U be some subspace of V. V is some finite dimensional vector space, and this is your natural projection, which means what? It takes a vector V to the corresponding coset, right? That map. This is of course a linear map. And suppose we have a subspace K bar of the quotient space. We are writing a bar above K just to emphasize that this thing is a subspace of the quotient. That's all. It's not like K has its separate identity and then we operated something on K and then obtained K bar. No. All I'm saying is that just fix a subspace of the quotient and directly call it K bar. Okay? All right. So then the conclusion is that the dimension of this subspace, this is a subspace of V, is equal to the dimension of K bar plus the dimension of U. All right. So K bar is a subspace of this guy, but U is a subspace of that guy, and it may look strange, but let's see. And I'm sure I must have given this kind of thing as an exercise at some point. I don't know, but anyway, let's prove it. So we have this map pi. This is obviously a surjective linear map. All right, and we have this subspace of the quotient K bar. All right, so what we can do is we can take its preimage under pi. Right? And now since this is surjective, this is also surjective, but surjective under which map? It's the restriction of pi to this particular subspace of V. So note that this is a subspace of V, and we can draw this arrow to make the diagram commute. So this is the inclusion map, this is the inclusion map. This is our map pi, and what is this map? This is also pi, but restricted to this thing. And writing both of them as pi may be confusing, so I will make this symbol. So when I make the symbol, I just mean pi suitably restricted. Suitably restricted meaning restricted to this domain that we have there. So this diagram automatically commutes. All right, this is a commutative diagram, and Yeah, so what is kernel of this map? Kernel of this is U, right? What is the kernel of pi? Kernel of pi is U, certainly, but same is the kernel of this map. Because anything that is in the kernel of this is also in the kernel of pi. So the kernel of this guy is contained in U, but since this is, the pullback of this guy, so the pullback of 0 is contained here, and the pullback of 0 is U. That's precisely the pullback of 0, and everything in U is definitely killed by this map. So this is a simple observation, and therefore by your first isomorphism theorem or whatever, this factors through the quotient right? So this is again your natural projection on this quotient, and this is the induced map. And since this is surjective, this is also surjective, and this is of course injective, just by the first isomorphism theorem. So this is an isomorphism. We're not doing anything new. It's just that you have a linear map whose kernel is given, so you can always factor out this way. And therefore the dimension of so these two dimensions are equal. And now we just use the fact that the dimension of the quotient is the difference of dimensions. And that's it. Once you rearrange, you get this. So it's a very simple argument. And let's move on. Right. So maybe I should hide it first. So fix an endomorphism on a vector space V, and suppose U is some T invariant subspace, and let T bar be the, what have I written? T bar be the induced endomorphism on the quotient. So what I wanted to write was T bar in be the induced endomorphism on the quotient. So then what we want to say is that the dimension of the kernel of the induced endomorphism is at most the dimension of the kernel of the original one. Okay. So let's try to show this. So first of all, we have this diagram. So we are proving it. We have this diagram. Right? And now what we have is we have the kernel of, so we have the kernel of T bar, which we will include via this inclusion map, right? So kernel of T bar is obviously a subset of this, so we have just indicated that here. This is the inclusion map. Okay, and we will pull it back by pi. So just give me 1 second. Yeah. So here again, pi should have been replaced by pi suitably restricted, and this is pi inverse kernel T bar. And that we include here. All right, so far everything commutes, nothing going on really. All right. So here is one observation. If you pick something here and you go here, then you go here, and then you go here, what do you get? You pick something here, you go to the kernel of T bar, and then you of course go to the kernel of T bar, and then you go to 0 because you're in the kernel of T bar. So in this path, anything that you start with becomes 0. So therefore in this path, the same thing should happen. So you come here, you come there, and then you become 0, which means when you reach this junction, you should be in the kernel of pi, but the kernel of pi is precisely u. So everything here is mapping into u, right? But this is the inclusion map, so we can make another diagram now, or rather we can just edit or add to this diagram. So this is u, and this is t suitably restricted, and this is the inclusion map. So what's going on? Once again, we notice that if you follow this path, you always land in u, but this was the inclusion map. So it says that this entire thing is mapping inside u under the map t. That's all that this is saying. So we can, depict that pictorially via this appendage. So this arrow is just the restriction of t to this particular subspace of V, that's all. And we know that since everything here under T maps to U, here we can write a U, and everything commutes. This entire thing is commutative. Okay. So this this has some dimension which we computed. So the dimension of or let's just apply rank nullity basically. So let me push this a little bit up. And now we are going to apply rank nullity to this guy. Let's apply rank nullity to that guy. So dimension of the domain of that guy is the dimension of the kernel of that guy plus dimension of the image. Okay. But we know what is the dimension of the left-hand side. The dimension of the left-hand side is dimension kernel T bar plus dimension of U. That is what we did in the previous page. Right? But this is less than equal to so we did two things. Kernel of this guy is obviously contained there. So this dimension is at most that dimension. And image of T bar is obviously contained there. In fact, I think it is just equal to it, but I don't need to know that. So this is contained there, and hence this dimension is at most that. Okay. So this, if you just, cancel out dimension u from both sides, you get the desired result. So that's it. That is a proof of this fact. Certainly you can write other proofs. You don't need to necessarily do this only. There are other proofs, but I find this very, very elegant. Okay, so now finally we can prove, so this is one more step, and after this we can come to our main result. So let T be some endomorphism on a vector space and fix a polynomial over the base field. So F is the base field of the vector space. We haven't written that. U be some T invariant subspace, and this be the natural projection map, and this be the induced endomorphism on the quotient. Fix some positive integer k. Then the dimension of kernel of this particular endomorphism, this is an endomorphism on the quotient, is at most the dimension of the kernel of this endomorphism, which is an endomorphism on the original vector space. Okay? This is like a one-line argument. One just needs to realize that this endomorphism is same as this endomorphism, which I need to explain what have I written. So this was an endomorphism on the quotient, and hence you can talk about this, and hence you can talk about this, and each of these are endomorphisms on the quotient. All right, this is an endomorphism on the parent, and hence this is also an endomorphism on the parent. And then we have put a bar on top. So note that since U is T invariant, since this is a T invariant subspace, it is also invariant under this guy. That is a very simple fact. And hence one gets an induced endomorphism on the quotient. So there are two seemingly different endomorphisms on the quotient. One is this one and one is that one, but they are exactly the same. And this is something that I leave to you as an exercise. There is nothing to it, just unravel the definitions. So once we have that, so now dimension of the kernel of this guy is equal to the dimension of the kernel of that guy, which is by the previous proposition less than or equal to that. And that finishes the proof. Right? This is at most that. That's all. And this is true for any k. Okay. So finally, fix an endomorphism on a vector space V. Fix a T invariant subspace, and T bar be the induced endomorphism on the quotient. Fix an eigenpolynomial of T bar. So then, the same thing is also an eigenpolynomial of T. And further, the geometric multiplicities behave this way. So the geometric multiplicity of this, eigenpolynomial of T bar is at most the geometric multiplicity of, the same polynomial. But here we have written a T. So just note that, these two things are different numbers. And we have this inequality, and same for algebraic multiplicity. Okay. So why, first of all, why is it true that if Qx is an eigenpolynomial of T, if Qx is an eigenpolynomial of T bar, then it is also an eigenpolynomial of T. So first, why is that true? So here is a fact which we should have recalled in the beginning, but anyway, let me state it now. So we know that the eigenpolynomials of any endomorphism are precisely the monic irreducible factors of the minimal polynomial of the endomorphism in question. This is something that we have proven earlier. All right, and the other fact that we have proven way earlier is that the minimal polynomial of the endomorphism induced on the quotient divides the minimal polynomial of the original. Right, and these two facts establish this. Why is that? So Qx is an eigenpolynomial of T bar, that is given, and hence Qx divides the minimal polynomial of T bar, so Qx divides the minimal polynomial of T bar, but minimal polynomial of T bar divides the minimal polynomial of T, and hence this is an monic irreducible factor of this guy also. Well, I should have written Qx. So Qx divides the minimal polynomial of T bar, this is how I should have written it. and this divides the minimal polynomial of t, and therefore this divides that, and hence qx is a monic irreducible factor of the minimal polynomial of t, which establishes that this is an eigen polynomial of t. Alright, and now we just apply the previous proposition. So to see this one, apply the previous proposition for k equals 1. So we know that dimension of the kernel of qt bar with exponent 1 is at most the dimension of the kernel of qt with exponent 1, which is same as saying the geometric multiplicity of q with respect to t bar is satisfying this inequality. And for algebraic multiplicity, it's a little bit, one more step. So let's do that in full so that there is no confusion. For the algebraic multiplicity, we have dimension of, or let's start with here. We have algebraic multiplicity of q with t bar is equal to dimension of the kernel of qt bar, and here it is dimension v mod u. Alright, which is at most dimension kernel qt dimension v mod u. So this is where we apply the previous proposition with k being equal to this number, but this is obviously less than equal to that, because this number is at this number is at most that number, and what we have here is the algebraic multiplicity. That's it. That proves the second part also in this part. But really the heart of the matter is this deduction, the fact that if you have an eigen polynomial of the quotient, then it is also an eigen polynomial of the parent, and then the previous proposition. So these are just then instantiations of the previous proposition. Okay. So yeah, I don't have anything more to say today. We will use these things subsequently, but I hope these were anyway interesting. Alright, so like, comment, share, subscribe, and I will see you next time.